Hi, these are the solutions to Wednesday's April 1st recitation problems. Um, the first question asks you to think about some ideas related to force and power. We're imagining an electric car. Those are nice because they say right on the tin how much potential energy they can convert into mechanical work and how many watts their motors can point out or can put out. So we know, oh, I should say before I get started that these ideas lead directly into homework 11. Um, So I know that if I'm driving at a constant speed on flat ground, that the power from the engine plus the power from drag has to equal zero. Air friction is taking energy away from the car. The motor is putting kinetic energy into the car. And if those are equal, then you go at a constant speed. Um, so the first question, the first thing we're looking at is find the rate that air drag does work, i.e. the power. So the power from drag is going to be force dot velocity. These are in opposite directions, so this will be negative. So we'll color code this. So that's going to force is minus gamma v squared because it's backwards, and the velocity is another v. So the power from drag is just minus gamma v cubed. Looking at part B. Part B is using this idea that I wrote down perhaps a little bit early. So I know that the engine power plus the drag power is 0. So I can substitute in what I know about the drag power. So PE equals gamma v cubed, where I've moved it over to the other side and removed the minus sign. So doing a little bit of algebra to solve for v. This gets me that v is the cube root of the engine power over the velocity. We don't see cube roots that often, but here we do. Continuing on to the next part, I've given you some values for a Tesla Model 3. So we're going to take the formula from before. So we know that the top speed is the cube root of the maximum engine power divided by the drag constant. Gamma here is just a value that tells you how much drag something has. It depends on the car's shape and size. So if I put those values in, engine power is 200 kilowatts divided by 0.8 kilograms per meter. Yes, that is in fact the right unit. To the 1/3 power. This gets me 63 meters per second. Let's convert that into units that we more commonly use for cars. This is 141 miles per hour, or in kilometers per hour, 227 kilometers per hour. And this sounds reasonable. The head of Tesla Motors is on record saying we don't make slow cars. 141 miles an hour is quite quick, but 200 kilowatts is a lot of power. So for part D, here we're asking how far could we go at this speed. So remember that work is force times distance. And we know the maximum amount of work that the car can do before it runs out of battery. That's equal to the potential energy in the batteries U. So I can say U equals force times distance, where D is the distance we're solving for. And we know that the force applied by the engine is equal and opposite to the drag force. The drag force is thus F drag, times d, and we know the drag force is gamma v squared. So if we want to solve for the distance, this tells us that the distance is, well, start over here on the left. Come on, stylus. So if the potential energy is gamma v squared d, then d equals potential energy over gamma v squared. And I have all of those values. I just found them. So let me now type those in. I have 270 megajoules divided by 0.8 kilograms per meter times 63 meters per second squared. So this gives me a range of 85 kilometers. Now you might say going 85 kilometers on one battery charge, that's not very far, right? But keep in mind this is going at 140 miles an hour, 227 kilometers per hour. So here in part E, we're going to do some proportional reasoning here. Note that the distance was the potential energy divided by gamma v squared. So if v goes down by a factor of 2, then d goes up by a factor of 2 squared, which is 4. So the answer here is 4 times further. So what we just calculated is that a Tesla Model 3 can go not 85 kilometers, but 85 times 4, or 340 kilometers, at half of its top speed, which is 113 kilometers per hour, or 70 miles per hour. And that's pretty respectable. You can go even further if you don't go as fast. On to problem 2. Problem 2 is kind of a classic work energy problem. It's here to get you a little bit of practice before we move on. Pardon the clicking in the background. This is messages from the staff Slack channel. So we have a ramp here. It's elevated at an angle theta. And we have an object compressed against a spring. So here's our spring. And this is compressed some distance d. I'll write that in later. So our object goes up, goes up, turns around, and comes back down. And for use in later parts of this problem, I'm going to label these positions as A, B, and C. And just to put everything in one place, at A, the velocity is 0. The spring is compressed. A distance d. At B, the velocity is also 0. The spring is at equilibrium. And finally, at C, the velocity is still 0, and this time the spring is compressed a distance b. Now, what we know is there is friction on this ramp. So the thing has a certain amount of total mechanical energy at A. And that's going to be greater than the total mechanical energy at C, since friction does negative work. And at both A and C, the only mechanical energy is in the compression of the spring. So that means that the elastic mechanical energy at C is less than the elastic potential energy at A, so B is less than D. One way to think of it is there's some amount of energy at the beginning. Some of it gets lost to friction during the motion, so there's less mechanical energy and thus less compression of the spring at the end. Part B asks us to figure out how far we go up the ramp. So I'm going to use the idea of potential energy here. So the kinetic energy at A plus the potential energy at A plus the work done by other forces, here I mean friction, equals the kinetic energy at B plus the potential energy at B. Now, to get the gravitational potential energy at B, we need to know its height. So if this distance here is L, then this distance is L sine theta. So I have no kinetic energy in either place. So filling in what these are, I have 1/2 kd squared. The work done by friction is going to be minus the force of friction times the distance that I go, so L, and that equals the potential energy at B, which is mg times L sine theta. L sine theta comes from what we just did, the trig. And here we need to find the force of friction, which is mu times the normal force, which is mu times mg cosine theta. Probably remember that from Unit 2. If not, draw a free body diagram and think about the motion perpendicular to the ramp. So this gives us that 1/2 kd squared minus mu mgl cosine theta equals mgl sine theta. Solving this for L, we get L equals 1/2 kd squared divided by mg sine theta plus mu mg cosine theta. For part C, we have the same thing, except now we're going back down the ramp. The problem tells you that you can use L in your answer, because I don't really feel like substituting in that mess up top. So now I have the kinetic energy at B, which again will be 0, plus the potential energy at B, plus the work being done by other forces, equals the kinetic energy at C plus the potential energy at C. Again, the kinetic energies, both of them are 0 because we're connecting 2 points where the thing is stationary. So now we have, whoops, wrong tool. Now we have mgl sine theta. The work being done by friction on the way down is again negative. This is important. Friction, when you're going down, points up the ramp. So in both cases, you have the frictional force opposing the motion. So minus mu mgl cosine theta equals 1/2 kb squared. Solving this for b, we get b equals, so I'm going to multiply by 2 and divide by k, and then take a square root. So I get 2 mg L sine theta minus 2 mu mg L cosine theta all divided by k. And that's problem 2. So this approach of kinetic energy plus potential energy at the beginning of the motion plus the work being done by other non-conservative forces equals kinetic energy plus potential energy at the end of the motion is how you can approach every work energy theorem situation that you have.